Welcome to a video on how to do vector operations, specifically when you have a grid to help you. Before we begin, we're going to discuss some common mistakes. So suppose you have a diagram that you have labeled with vector name A and vector name B with the little arrows on top to indicate that they are vectors. And if you were given some sizes, let's say 5 and 3, you cannot just record a vector is equal to 5 because 5 is a scalar. It doesn't have a direction on it. And A is supposedly a vector. So the only way to fix this is to record it properly by including absolute values on the magnitude symbols on each vector, so that this is now a true statement that scalar magnitude is equal to a number 5 or 3 in the other case. Second mistake is if you're trying to think of vector addition, you cannot just assume that you add 5 plus 3 magnitudes and you would get your answer, because vectors have directions. Only in one specific case can you actually just add the magnitudes. So once more, I'll just say vector is not equal to a scalar, and we'll discuss in detail how to deal with vector addition depending on the angles next. So here is a summary of how to deal with finding that addition of A plus B vectors depending on where the angle is. And please note that theta that's always provided is going to be between two tails at all times. So if angle is 0 degrees, that means between the two tails there's no angle or 0 degrees. To be able to add them, we're going to put A over here, so it's head to tail. So the resultant is A plus B, a longer version. So this is the only scenario where magnitudes of A plus B is a pure addition between the magnitudes of original vectors. However, if the angle between the two tails was 90, for you to be able to find vector A plus B, because they're right now oriented tail to tail, we can draw a parallelogram as shown. And the resultant would be pointing from the tails to this opposite diagonal. To find the length of this, as you could tell that this is forming a right angle triangle, we can use Pythagorean theorem to find that resultant's magnitude. Next, we have angle 180 degrees between the two tails. So that means the vectors are going at opposite directions. Again, we can move in vector A, so it's head to tail with the other vector. And the resultant would be this tiny portion of where you started to where you ended up. So it's going to be shown over here as this is the resultant vector. So in this situation, the addition of A plus B vector magnitudes is actually going to be a subtraction between the two magnitudes. Finally, if we have some other random angle between the two tails of the vectors, you most likely already have an idea that this will involve probably the cosine law somehow. So if you were to draw using parallelogram law the resultant vector, unfortunately that angle right here is going to be cut by this resultant. Do not make an assumption that it's going to be cut straight in the middle, because it all depends on the lengths. So here's my suggestion. So you can set up the cosine law, but instead of putting theta here for your cosine law, what I'd like you to do is think of the C pattern over here. So this C right here, this up, over, creates a C, and we know that those angles are supplementary. So whatever theta is, 180 minus the theta will be the angle in this yellow triangle, and that you could use inside of this cosine law. So as a recap of all of these, you could tell that in this scenario with angle 0, you do have a pure addition for the magnitudes. In this scenario, you had to use Pythagorean theorem for the magnitudes. And if you were asked for angles, most likely TOA is the easiest choice. If you have 180 degrees between two tails, it ends up being a subtraction. So as you can tell, you can't just memorize, you have to draw a picture. And then this last one is sine law or cosine law. A quick note about sine law. If you have side-side angle provided for you, that creates possibly an ambiguous case when you're trying to find another angle. Sine inverse will never give you an obtuse angle. So if your diagram looks like it's going to be obtuse, I would suggest that you use cosine law in that situation and avoid sine law. Okay, here's an example how to use a grid. So this question is to find the vector r, which is a resultant of 3c's minus b. So here is my 3c's head to tail. So it's as if one longer vector pointing down. My vector b in opposite direction because it's a negative b that we're trying to add. Here's the resultant. Now for the next part, I'm going to get rid of my rough work. I'm going to keep the resultant. And this part, I'm going to use the grid to count how many vertically squares I have and how many horizontally. So here we have 4, here we have 1. So if I wanted to find a vector means I need to find the direction and magnitudes. Let's start with the magnitude. So vector r, notice absolute value symbols to indicate this is just the magnitude. You could use Pythagorean theorem because that forms a right angle triangle with the grid. So here we get root 17. For me to find the angle, suppose I put theta right there, and then I can use SOHCAHTOA, specifically TOA, because we have opposite and adjacent side. And so doing this calculation, we get 14 degrees. Next, in our final solution, we want to state vector r. Notice now it doesn't have absolute value on it because now it's a full vector that has the magnitude and the direction, except I don't have the direction fully filled in. You could quote vectors in relation to a regional vector c or vector b. I'm going to show you both. So remember, quoting angles is always between two tails. So resultant we have already, and this vector c, we want it to be right beside it tail to tail. We already know what this theta is, so that one's easy, 14 degrees. Then we place vector b tail to tail with vector r, and in this situation we have to add 14 plus this 90 degree plus 45 degree. Why is this 45 degree angle, you might ask? Well, this size horizontally is size 1 square and upwards is also 1 square. So it's an isosceles right triangle, which will have 45 degree angle. And so when you add them all together, 14 plus 90 plus 45 gives you the angle to the tail of vector b. Okay, and I'll just do one more example. Very similarly, here we have 2a's minus 3b plus c. We need to state the magnitude, and this time they ask you for the angle only for to vector c. So we have 2a's. So here's my first a, second a. Notice how I'm keeping down 1 over 2 consistent, down 1 over 2, like the original. Then we have 3b's with a negative. So I need to reverse the order of my b. Instead of going to the right and up, I'm going down and to the left. So we have down 1 over to the left 2, and I repeated it 3 times. Last part is plus c. So here's my plus c, organized head to tail with all of them. So think of this as a path to travel. You're starting from here. Where do you end up with? And this long path doesn't matter. It's the actual final result that matters. That's why we call it the resultant. And again, in order to find out the magnitude, we can get rid of this rough work and just think about this resultant itself and how many squares do we have vertically and horizontally for this resultant. So to find this magnitude, we can use Pythagorean theorem. To find the angle to vector c, we have to locate this vector tail to tail with the resultant vector and find this theta. Now, you could transfer this theta by Z pattern, alternate angles if you wished, to put it over here. So you could use SOHCAHTOA on this triangle that's already drawn for us. And so tan theta would be equal to opposite, which is 5, adjacent, which is 4. Solving for that, you get theta is 51 degrees approximately. And then your final statement, remember when you're quoting vectors, make sure you have a vector symbol. And if it is without absolute value on it, meaning it's not just a magnitude, you have to put the magnitude and the direction. And in this case, they asked you to do it in relation to vector c. So that's 51 degrees to vector c. Now let's discuss how to do this question if there was no grid. In other words, it's actually going to end up being quite longer. And I'm just going to briefly discuss the main steps, but I'm not going to solve it all the way. So I'm going to transfer our picture to be without the grid. Now, because if there is no grid, then you would have to be provided the magnitude in the direction of the original vectors. So the magnitude of this red one, vector A, would be √5, and the magnitude of B would be the same. And I found that just using Pythagorean theorem on the size 2 and size 1 triangle. And then the angle over here as well as here would be 27. And for vector C, it's just this way 2 units. Okay, so if you had to do this the long way, you'd have to find the resultant magnitude of this triangle here. That's drawn in yellow. Then you'd have to transfer the angles at the tails. Here would be 27, and at this head and that tail would be 27, 27. So now you would have a full angle within this yellow triangle. Because there's 2 vector A's, then the magnitude of this yellow triangle on this side would be 2√5, and here would be 3√5. And so you'd now have side, angle, side, for which you could use cosine law. So to find magnitude of R1, you would use cosine law. I forgot to put a little 1 over here for resultant version number 1, because it's not final resultant yet. For angle alpha, which I placed over here, you could use sine law at that point. And I chose alpha first, not beta, because beta could have been obtuse angle there. So I'd like to avoid ambiguous case. So I chose to find alpha first using sine law. And then to find beta, all you have to do is use angle sum property of triangles. All angles in a triangle add up to 180 to find whatever beta would be. Then, because this is not finished, you would have to then find out this resultant number 2, which would be the final resultant of all of these vectors, the red ones added with the blue ones with the green one C as well. And then in this situation, what you would do, looking at this yellow triangle now, for this gamma angle, you could think of it as the Z pattern over here. So this green line is parallel to this dotted line over here. So by Z pattern, we know alternate angles would be equal. So 27 plus beta would be the gamma. And then you would have side angle side, because you have this is size 2. This you would have found before, and now you have this angle in between. So you could use cosine law for resultant number 2 magnitude. And then you could find this delta. This is a Greek small case delta symbol using sine law again. So as a comparison, if you look back to how we've done it with the grid, we had much simpler calculations. We had Pythagorean theorem and just TOA to work through. Now, why do I talk about the grid method? Because I think of it as a prequel to algebraic vectors, which is going to be our next unit. So here's just a little preview. You won't understand how I did everything, but just kind of look ahead, and then you'll have a lesson on that in the future. So on this side here, I have geometric versions of this original question, vector A, B, and C, as you can see written here. And I've tried to put in the angles always relative to the positive x-axis, because otherwise this formula that you'll be learning would not work as neatly. I'm going to just briefly discuss this 2, -1. So algebraic vectors are the ones where you place some sort of coordinate system for your vectors, and you usually think of the origin as being where the tail is. So imagine if the origin was right here, you could say, well, I'm going to the right 2 and down 1. So algebraic version of this vector will look like a point. It's not really a point, but it's going to be 2, -1. For vector B, if you imagine the origin was at the tail of B, you're going over 2 up 1. So you'll have 2, 1. And by the way, notice how all of this, sine and cosine, so cosine of this angle from positive x-axis, would actually end up giving you exactly this 2. This 27 actually is rounded, so that's why I put in equals with approximation symbol on it. But you can actually use the original value for 27 with all the digits there, and you actually will find it's exactly going to end up as 2. So anyways, back to this, we have cosine here, cosine here, cosine here, and it's always of the angle relative to the positive x-axis. So it's negative angle when you're going clockwise, and positive angle when you're going counterclockwise. You will learn that in the next unit. So what am I trying to show you here? If you had algebraic vectors, then the way to add this 2a minus 3b plus c ends up very, very simple. You would get -4, -5 in the end. As you can see, if the origin was at the tail of our resultant, we'd be going over to the left 4 and down 5. This is what it's saying. So as a recap, this is the longest way to do this type of question. Geometric way, if you don't have a grid, you'd have to use sine and cosine law, maybe multiple times. If you have a grid, then it's a stepstone to algebraic vectors. You have Pythagorean theorem because you have right triangles here and SOHCAHTOA that you could use. With algebraic vectors, it ends up being even simpler. So you have to kind of look ahead and maybe anticipate the shortcuts that you will be able to use with algebraic vectors in the next unit.